So we want to cover the last couple of topics here, like Linda said. We're going to bring you the principles of multiple populations, the principles, the ideas of multiple indicators, without getting into details of the fitting, just so you can see what the promise is, what kinds of techniques are available, without having to understand the details of it. And then I can't resist to show you a couple of embedded growth models, but that'll just take 5 to 10 minutes. So I'll do the multiple populations. Linda will start and I'll start the multiple indicators, right? I'll do both. All right. You got yourself a deal. All right, I like that. All right, so multiple population modeling, what is it? And how do you do it? You have these cases. You can have a group variable, by which I mean, say, a gender dummy variable or a treatment control dummy variable as a covariate, namely as a dummy variable then. Or you can do something that we spent quite a lot of time on in day 1, multiple group analysis, topic we cover within the structural equation modeling day that will take place sometime in March 2008 here in this room. Or you can do a multiple group analysis of a special kind tailored to randomized interventions. Although that last approach, which I call the Mutean-Curran approach, for reasons that will become clear shortly, mainly because those were the people who worked on it, is now superseded, I would say, by growth mixture modeling approaches to randomized interventions. And I'll say a few words about that. But here are the ideas. So you have a situation where, say that you have a treatment control variable, just to jazz it up and talk about since we have a preventive intervention center here, a PIRC, Preventive Intervention Research Center, let's bring in a dummy variable that's treatment and control. And let's say that we have a growth model, 5 time points. Let's say that this is the pre-intervention time point, number 1 here. Fall of 1st grade, and the intervention takes place thereafter. So it takes place here, and these are post-intervention measures. Growth modeling is an excellent tool for studying effects of interventions, where you don't just do the regular ANOVA, looking at pre and post measures and looking at to see if the post-test means are different between treatment and control, but instead you let the intervention be something that influences the whole growth development. So the intervention influences the slope in your linear growth model. So it influences the development, and you want to see if there's significant influence of the treatment on that slope. That is your intervention effects in the longitudinal type of thinking. And you don't have an intervention effect here because you have randomized the intervention to individuals, and therefore the mean of this variable should be the same in the treatment and control group. So already you're seeing a couple of features here. Treatment effect should yield mean differences in the slope for the 2 groups, and it should not yield mean differences for the intercepts in the 2 groups, because pre-intervention we have statistically equivalent groups, same mean. So we're talking about differences between treatment and control groups in the means of these variables. This model, though, is quite limited when it comes to multiple group analysis because it says, for instance, that the variances are the same. The variance in development is the same for treatment and control group. which may not be the case. The growth curve, which is determined by by the relationship between these latent variables and these observed variables, for instance, through the time scores, are the same for treatment and control. The residual variances up there for the outcomes are the same for treatment and control. So there is the alternative approach of multiple group modeling, where those restrictions can be relaxed. So in a two-group model, you can have treatment or control and treatment, and any parameter may be different across the two groups. So a two-group analysis implies that you have a simultaneous analysis of all of the groups. So your data is, in this case, you have 4 or 5 columns, and all of the control group people, followed by all of the treatment group people, do a single analysis of all those people, where you can allow for differences in parameters between difference in any of these parameters across the two groups. Of course, it would only be relevant to do a joint analysis if some of the parameters were the same across the groups, because only then would you borrow information in estimating. For instance, the initial status mean can be estimated by everybody, treatment and controlled individuals, because they're assumed to have the same mean before treatment. And that will benefit the precision of estimation of that parameter. Whereas other parameters, particularly this one, mean and variance, perhaps should be different. The mean and variance for this is contributed by the treatment group people. Mean and variance of this is estimated with the help of the control group people. So in a nutshell, that is multiple group analysis. This could be males and females. And if you come from a CFA framework, this is old hat. This means that you're interested in testing things like measurement invariance. Does this measurement instrument of yours function the same way for males as for females? Particularly, are the factor loadings the same? Are the measurement intercepts the same? And only if the measurement instrument works the same is it relevant to compare the distributions of the latent variables across groups. See if the mean is higher here than here. You can only make that statement if you know that you're measuring the same thing, which relies on measurement invariance. So in day one, in the afternoon particularly, we spend quite a lot of time talking about multiple group analysis. And it's very relevant in growth modeling as well, where you could do, say, a study of gender development, gender differences in development, where every parameter can be different across the genders. Whereas in this case, essentially only the means can be different. So multiple group modeling is a more flexible tool than bringing in group as covariate, although it is more advanced and more demanding on the analyst. So it has pros and cons. And this looks way too complex for this time of the day. Here is an interesting application of this that is specific to longitudinal modeling. I don't know why all the laser pointers migrate over to this right side here. Now, if you look at this long enough, it will confess to you what it means. So you have here the 94 here, for instance, means 1994. So it means the year of measurement. 57 means 1957, the year a person was born. So you have people born in 1957 all the way up to 1964. 18 through 37 at the top row here is the age of the individual at the time of measurement. So for instance, in 94, the people who were born in 61 were 33 years of age. This is a good way of displaying multiple cohort data, and the advantage of multiple cohort designs is that you can study a relatively long time range of development from 18 to 37 in a relatively short span of real time. In this case, from 82 to 94. The distance between 1982 and 1994 is shorter in years than between 18 and 37. Your task tonight will be to figure out what the difference is. But essentially, you shorten the time span so the PI of the project doesn't retire before the study is written up. So you have 8 cohorts here. The more cohorts you work with, the longer time span you can study. But the more cohorts you have, the more strain is there on the assumption that is necessary that you have parameter invariance across the cohorts. So again, the gender invariance of parameters comes through here too. Optimally, the same growth model should hold for those born in 57 as those born in 64. But the difference here may correspond to societal changes to the point that parameters may change. Parameters change as a function of society and other things. So you don't want to have too many cohorts. So you have to balance the number of cohorts against that assumption. So if you have multiple cohort data, which I would urge you to collect if you're serious about collecting longitudinal data, you have this situation here where if you say that you take the wide approach, here's a little thinking experiment, and this is what we're going to do. We're just going to think together, not get into the details of setups. If you take the wide approach, then you would have, as columns in your data, one approach would be 18, 19, up to 37. So those would be the columns of your data. You look at certain outcome Y for each of those ages, Y18 up to Y37. And the rows of your data would be all the people born 57, all the people born 58, etc. What would that mean then? Well, if you look at this carefully enough, you see that you have dark areas, meaning not measured. This person born in 57 was measured in 1982, but was not measured in 81 or 80 over here, right? So it's only the cells with numbers in them, years in them, where we actually had measurement. So you had 4 measurements in a row here, skipped 2 years, funding was canceled, and then 88 and 89 and then 94, and then the study died. This is actually real data, NLSY, National Longitudinal Study of Youth, with an alcohol supplement from NIAAA. Unfortunately, it didn't go beyond 37. I think that would be useful. But in any case, my point is, if you analyze this as in wide form across time with data treated as a single group of people, you would have an awful lot of missing data. All of this is missing. All of this is missing. And you would most likely get a lot of problems of convergence because of low coverage issues, particularly if you want to test against an unrestricted H1 model, which SEM folks are fond of doing. Now, an alternative to this is to take a multiple group approach. Say instead that you have 8 groups of individuals, 1, 2, 3, 4, 5, 6, 7, 8. You can still assume that all 8 have all of the parameters equal, which is what you would do if you treated them as a single group, right? So all growth parameters behind this development held equal. But what you would buy is that you would then instead have only 1, 2, 3, 4, 5, 6, 7 variables instead of the many more variables, 18 to 37. So every group would only have 7 variables, measured in 82, 83, 84, up to 94. 7 variables for each group, and you would avoid all this missingness by design cells that you have here. So that's a much simpler approach, and that then opens up the possibility to test the assumption of invariance of parameters across cohorts, which may or may not be true. So you can relax those assumptions, and that will be okay, at least if the non-invariance of parameters across cohorts is with respect to relatively uninteresting parameters. In this case, we study alcohol consumption, and one of the parameters that was not invariant was the mean of a covariate, starting drinking early, and that is not a key parameter of the growth model. But if you have growth factor parameters that are not invariant, well, then you would have to acknowledge that some cohorts follow a different growth process than others. And therefore, you can't really say it's the same growth process over all of the years. But the multiple group approach is what we recommend for multiple cohort analysis. And the next couple of slides give you a couple of ideas of how to do that, although we don't have time to talk about that today. So that's the multiple cohort here. And you have the input for it. Another application area for multiple cohort analysis is in the context of what this center, Nick Alongo's center, is all about, preventive interventions and randomized trials. And for those of you interested in that, you should know that there is a so-called Prevention Science Methodology Group, PSMG, that talks quite often on the phone, conference calls on Tuesdays, and discuss applications of methodology having to do with interventions, particularly randomized field trials. And developmental epidemiology comes into play here quite a lot, and it has a very flowery language where you talk about risk levels, variation in risk and protective factors, and developmental path within a defined population in the absence of intervention. And our task as methodologists will be then to sit and nod and smile and try to translate that language into statistical modeling. And it says they have a growth model for the control group. And they have covariates. That's the risk and protective factors. Absence of intervention is the control group behavior. Developmental path means growth modeling. Okay, so covered that. And then directed intervention at these risk and protective factors in an effort to change the developmental trajectories in a defined population. That says that Tx influences S. Okay, so bring that into model. And then evaluation variation in intervention impact across risk levels and context of proximal and distal outcomes there by testing. So that is multi-level modeling, multi-level growth modeling, which we'll do tomorrow, including a distal outcome, which means an outcome that happens after the growth process, like high school dropout. So we cover this with growth modeling quite well. Here's a paper, if you're interested, in Psychological Methods, a journal I recommend for typically quite applied methodology papers. And it was applied to data from Baltimore public schools carried out by the Johns Hopkins Prevention Center led by Shep Kellum at that time. And randomizing treatment on the classroom level in Baltimore public schools, which is no small feat. But I won't talk about this more than to say that it uses a teacher-rated instrument for child's aggressive, disruptive behavior, breaking rules, harming property, etc. in the classroom. And some of the examples that we worked with draw on these data. And the most important scientific question was whether the good behavior game reduces the slope of this aggression trajectory across time. So that's what we were looking at on the right here. And also whether the intervention varies in impact for children who started out as high aggressive versus low aggressive. So a treatment baseline interaction question. And that's what this Mutien-Curran paper is all about, treatment baseline interaction questions. Now, we won't go into that example except to say that if you have these sort of data, you may want to look at this article and look at the steps in the multiple group analysis. First, you look at the development in the absence of the intervention. That is the normative development in the control group. Then you do the analysis in the treatment group. And then you do a multiple group, i.e. a two-group analysis. And with or without interactions here has to do with the treatment baseline interaction modeling. Sensitivity analysis, and then a power analysis having to do with sample size and your ability to detect intervention effects if they're there. And just give you 2 slides on this. Here it is, the development from fall of first grade up to, I think, grade 7 or 9. And aggressive behavior scale on the y-axis. And the results can be summarized as pairs of curves. This is the normative development in the open symbols. and here's the intervention development. So we see that the intervention reduces the level of aggressive behavior, its development. The control group development is higher. So there's a beneficial treatment effect for those who started high in fall or first grade in terms of aggression. It's much less effect for those who started medium, and no effect really for those who started low. So that's a treatment baseline interaction, because most often in our intervention studies do we find intervention effects for certain subgroups. Very often do we find no main effects. And we need to have techniques that can pull out subgroups that benefit from the intervention. So answering the question for whom an intervention is effective.